Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is unbalanced Y configured loads. Our objective is to examine the electrical properties of unbalanced 4 and 3-wire Y configured loads in 3-phase AC systems. This lecture operates under the presumption that the viewer has more than a passing familiarity with 3-phase AC and analyzing balanced Y configurations, as illustrated in the Balanced Y Configurations lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. 3-phase AC circuit analysis is often preceded by the foreboding statement, "Abandon all hope, ye who enter here," and in no scenario is this warning more frequently applied than to unbalanced loads. Reputable textbooks regularly contemptuously dismiss the topic with something like this: "Unbalanced 3-phase AC circuit analysis is beyond the scope of this manual. Here, check out mesh analysis. That should keep you busy for a while," before they hurry home, lock their doors, and hide under the bed, as if unbalanced load analysis was some coked-up tiger with a hunger for man-flesh that prowls the streets at night looking for nerds to eat. Don't believe the hype. Watch me walk up to this tiger and poke it in the eye with my special eye-poking stick. Unbalanced load analysis is not nearly as hard as it's made out to be, and you already have the skills you need to similarly poke this tiger in the eye and remain unscathed. Join me if you will. Before we begin, it may help to remind ourselves of the properties we discovered regarding balanced Y configurations in the aforementioned lecture. If you recall, a balanced 4-wire Y configuration is comprised of 3 identical branch impedances and uses a 4th neutral wire linking the 3-phase AC source and the load. Each identical load impedance in a balanced 4-wire Y configuration experiences the line to neutral voltages. Given identical loads and identical voltage magnitudes, load current magnitude and relative phase shift would be the same. Current in a particular line would be equal to the current through that particular element. Given identical loads, identical voltage magnitudes, identical current magnitudes, and identical relative phase shift, each load impedance would experience the same apparent, the same real, and the same reactive power. Finally, for a balanced 4-wire Y configuration, current in the 4th neutral wire is a summation of I1 plus I2 plus I3. In the balanced condition, no current travels through the neutral line, and we can effectively eliminate it from consideration if we wanted to. Finally, total apparent, total real, and total reactive power consumed by the complete circuit will be the summation of each branch impedance apparent, real, and reactive power. Lacking a 4th wire, carrying no current, one can retroactively apply these same properties to a balanced 3-wire Y configuration as if it was a balanced 4-wire Y configuration, simply lacking the 4th wire. What do all these ground rules mean with respect to 3-phase AC circuit analysis strategy for balanced loads? It means the analysis of balanced loads is extremely easy. Do a single Ohm's law calculation, then appropriately phase shift it for the remaining phases. Then do a single AC power calculation using only the relative phase shift between voltage and current and multiply it by 3 to get the total power. Move on. You'll be absolutely overjoyed to realize that most circuit analysis scenarios involve balanced load configurations, including common industrial applications like shop heaters and industrial 3-phase AC motors used to drive pumps, turn fans, or perform other industrial tasks. Again, these observations are true if and only if the 4 or 3-wire Y configuration under inspection is balanced, in that each branch impedance is identical and that the excitation voltages for the 3-phase AC system are similarly identical, only differ in phase shift by 120 degrees. Unbalanced conditions, in contrast, necessitate a little bit more inspection. An unbalanced load, as the name implies, is one in which the branch impedances comprising the Y configuration do not exhibit identical impedance magnitudes or angles. Let's take a look at an unbalanced 4-wire Y configuration first. Unbalanced 4-wire Y configurations necessitate only a minor modification of our earlier observations for balanced 4-wire Y configurations. Let's start with the basics. Obviously, given different branch impedances, we might expect different current magnitudes and/or phase shifts in each branch. Consider the interaction of these 3 currents. An application of Kirchhoff's current law demonstrates that current IN equals the summation of I1 plus I2 plus I3. For balanced conditions, the 3 balanced load currents effectively cancel each other out, such that current in the 4th neutral wire equals 0, For unbalanced conditions, IN still equals the summation of I1 plus I2 plus I3. However, given different current magnitudes and/or phase shifts, we might expect these currents to no longer summate to zero. As such, any degree of imbalance current inside the Y configuration is carried away by the fourth neutral wire. The additional wire in a 4-wire Y configuration also does something else mightily important. By directly electrically coupling the 3-phase AC source to the Y-configured load, it ensures every single load in the unbalanced configuration still experiences the line-to-neutral differentials. As we'll learn in a moment, this is not true for an unbalanced 3-wire Y configuration, where any imbalance current is left to circulate throughout the system, such that even voltage across individual elements is imbalanced. In this sense, I like to think of the additional 4th wire as kind of a relief path, where any imbalance current is shuttled away from the Y configuration. Again, the important points being that for unbalanced conditions, each load still experiences the line-to-neutral voltages, and IN equals I1 plus I2 plus I3. Current in the 4th neutral wire is no longer zero, and any imbalance current is carried away. Let's try an application of these principles. Consider a 120, 208 volt, 60 Hz 3-phase AC source supplying power to an unbalanced 4-wire Y configuration. Load impedance Z1 has a magnitude of 535 ohms at an angle of 51 degrees. This is the odd man out. Load impedance Z2 has a magnitude of 365 ohms at an angle of 28 degrees. And finally, load impedance Z3 also has a magnitude of 365 ohms at an angle of 28 degrees. This is the definition of an unbalanced load. Impedance Z1 has a different magnitude and angle than either Z2 or Z3. Recall that industrial 3-phase AC motors are ordinarily modeled as balanced loads. Given load impedance Z2 and Z3 are identical, this might be some motor that experienced some localized thermal or mechanical stress, or perhaps is just made poorly, such that winding 1's impedance appears altered. This motor might not draw the same current, and as such, neither consume nor exert the same amount of power as it would in the balanced condition. Current through the different load impedance Z1 might be different than that experienced by load impedance Z2 and Z3. Any imbalanced current will travel in the 4th neutral wire. This being said, the 4th neutral wire ensures each branch impedance still directly experiences the line-to-neutral voltages. Source L1 establishes a differential of 120 volts at an angle of 0 degrees between L1 and neutral. Load impedance Z1 goes from L1 to neutral. It makes sense then that the voltage across load impedance Z1 is 120 volts at an angle of 0 degrees. Similarly, source L2 establishes a differential of 120 volts at an angle of negative 120 degrees between L2 and neutral. Load impedance Z2 goes from L2 to neutral. It makes sense then that the voltage across load impedance Z2 is therefore 120 volts at an angle of negative 120 degrees. Finally, source L3 establishes a differential of 120 volts at an angle of 120 degrees between L3 and neutral. Load impedance Z3 goes from L3 to neutral. It makes sense then that the voltage across load impedance Z3 is therefore 120 volts at an angle of 120 degrees. Current in line 1 would travel through load impedance Z1 and then return via the neutral connection. Similarly, current in line 2 would travel through load impedance Z2 and would return via the neutral connection. Finally, current in line 3 would travel through load impedance Z3 and return via the neutral connection. A Kirchhoff's current law analysis of IN suggests that IN equals I1 plus I2 plus I3. In summary, each impedance element in this unbalanced 4-wire Y configuration still experiences a line-to-neutral voltage, and current in the line equals the current through the load. These are the most fundamental aspects of 4-wire Y configurations, balanced or unbalanced. An application of Ohm's law for load impedance Z1 demonstrates current through it will be 224.3 milliamperes at an angle of negative 51 degrees. The phasor diagram illustrates current lags voltage by a relative 51 degrees. Application of the AC power formula demonstrates load impedance Z1 experiences 26.9 volt amperes of apparent power, of which 16.9 watts is directed towards real power and 20.9 vars is directed towards the reactive interchange. Similarly, an application of Ohm's law for load impedance Z2 demonstrates current through it will be 328.8 milliamperes at an angle of negative 148 degrees. The phasor diagram illustrates current lags voltage by a relative 28 degrees. Current through load impedance Z2 is of a different magnitude and relative phase shift than current through load impedance Z1. This is to be expected given unbalanced impedances. Using only relative phase shift, application of the AC power formula demonstrates load impedance Z2 experiences 39.5 volt amperes of apparent power, of which 34.8 watts is directed towards real power and 18.5 VARs is directed towards reactive interchange. Load impedance Z2 experiences a different amount of apparent, real, and reactive power than load impedance Z1. This is again to be expected for unbalanced impedances. Impedance Z3 is essentially a repeat of impedance Z2, only phase shifted by a relative 120 degrees. An application of Ohm's law for load impedance Z3 demonstrates current through it will be 328.8 milliamperes at an angle of 92 degrees. A phasor diagram illustrates current lags voltage by a relative 28 degrees. Using the relative phase shift, application of the AC power formula demonstrates load impedance Z3 experiences 39.5 volt amperes of apparent power, of which 34.8 watts is directed towards real power and 18.5 VARs is directed towards a reactive interchange. Given these observed electrical properties for load impedance Z2, Z1, and Z3, let's now examine total apparent, total real, and total reactive power for this complete circuit. Note, for unbalanced load conditions, one cannot simply multiply an individual branch power figure by 3 because they're no longer identical as it was for the balanced condition. To further complicate matters, one cannot even numerically summate individual apparent power magnitudes. Remember, apparent power can be considered as having both a magnitude and a direction because it consists of real and reactive dimensions. One must account for apparent power angle when performing summations. For this reason, it's perhaps easier to solve for total real and total reactive power first. Total real power equals the summation of individual real powers. Substituting in our given values yields a total real power figure of approximately 86.6 watts. Again, note, for unbalanced conditions, one cannot simply multiply an individual branch real power figure by 3 because they're no longer identical. Similarly, total reactive power for this system equals the summation of individual reactive powers. Substituting our given values yields a total reactive power figure of 58 VARs. Again, note, for unbalanced conditions, one cannot simply multiply an individual branch reactive power figure by 3 because they're no longer identical. Given the total real and total reactive power, we can now package these as the real and imaginary components of a rectangular number, as 86.6 watts plus J 58 VARs, and then convert it to polar form as 104.2 volt amperes at an angle of 33.8 degrees, which yields our total apparent power figure. Let's now examine current in the neutral line for an unbalanced 4-wire Y configuration. Our previous Kirchhoff current law analysis of IN suggested that IN equals I1 plus I2 plus I3. Substituting our given values yields IN to be approximately 150.5 milliamperes at an angle of negative 172.4 degrees. For your visual thinker, the phasor diagram of all the currents shows that IM appears to be the offset or imbalance for the 3 branch currents. If this visualization doesn't do the trick, it may be helpful to remind ourselves what a phasor really represents. You recall, phasor equivalents are simply shorthand representations for time-variant sinusoidal equivalents. Plotted as a function of time, sinusoidal voltage across and current through impedance element Z1 would look something like this. Assuming L1 is our reference, current through Z1 lags the voltage across it by a relative 51 degrees. Similarly, when sinusoidal voltage across and current through impedance element Z2 is plotted as a function of time, it would look something like this. Assuming L1 is our reference, L2 lags L1 by 120 degrees, and current lags our assumed reference by 148 degrees. This being said, current through Z2 still lags voltage across it by a relative 28 degrees. Finally, when sinusoidal voltage across and current through impedance element Z3 is plotted as a function of time, it would look something like this. Assuming L1 is our reference, L3 lags L1 by 240 degrees, or more appropriately, leads it by 120 degrees, and current leads our assumed reference by 92 degrees. This being said, current through Z3 still lags voltage across it by a relative 28 degrees. When you superimpose the plots of current as a function of time on top of each other, we notice something interesting. I1 is not only a different magnitude than I2 and I3, doesn't exactly fit in the spot I2 and I3 politely reserve for it, and is instead rudely sitting in their laps. At any moment in time, the instantaneous values of I1 plus I2 plus I3 yields a remaining amount of imbalanced current, in this case 150.5 milliamperes at an angle of negative 172.4 degrees that's channeled away via the fourth neutral wire. Before we move on, please make a quick note of the values we obtained in this exercise featuring an unbalanced 4-wire Y configuration. We'll do a quick comparison of balanced and unbalanced 4 and 3-wire Y configurations before we close out this lecture. In summary, unbalanced 4-wire Y configurations are not that hard, principally because of the existence of the fourth neutral wire. I like to think of it as a relief path for imbalanced current. Additionally, the fourth wire ensures individual branch impedances, despite their unbalanced nature, still directly experience the line to neutral voltage. We rather quickly demonstrated that this tiger does not have teeth, and we can dispatch it with no special skills. If only unbalanced 3-wire Y configurations were this easy. This being said, they're not that hard. Allow me to demonstrate.